Hi, this is Jawata Afnan, a PhD candidate in Integrated Program Neuroscience at McGill University and a 2021 CONP scholar. Here I'm going to present my work on mixed source imaging of resting state oscillatory patterns in healthy subjects and validation with intracranial EEG atlas of healthy brain. EEG mixed source reconstruction is an ill-posed problem and thus requires validation, especially before considering resting state connectivity analysis for clinical applications. In this work, we aim to assess resting state mixed source imaging of oscillatory patterns in healthy subjects, and our ground truth is intracranial EEG atlas developed by Prosher et al. 2018. This study provided the first atlas of intracranial EEG data for healthy brain by pulling together data from different patients with epilepsy, but from healthy regions of brain in eyes closed and wakefulness condition. This provides a unique opportunity to study spectral characteristics of normal brain oscillations at a group level. Method. We have this ground truth intracranial EEG atlas with total 1772 intracranial EEG channels coming non-uniformly from 106 subjects and labeled in 76 regions of interest. Each of these channels has 60 seconds of data sampled at 200 Hz in eyes closed condition. For MEG, we have data on 30 healthy subjects with same eyes closed condition. After standard pre-processing on the sensor space data, we perform mixed source reconstruction. To solve the inverse problem, we apply maximum entropy on the main method, which is a method developed by our group with collaboration with Dr. Jong Machlina in the context of EEG mixed source imaging. The key feature of this method is its sensitivity to the spatial extent of underlying sources. We apply a version of MEM called wavelet-based MEM, which is dedicated to localizing oscillatory patterns. From the reconstructed source maps, we go back to intracranial EEG space by applying a method proposed in Grova et al. 2016 to estimate virtual intracranial EEG on each of the intracranial EEG positions provided by the intracranial EEG atlas. For spectral analysis in each of the ROI, we calculate spectral density for intracranial EEG and virtual intracranial EEG. For intracranial EEG by averaging across all the channels within the ROI of intracranial EEG atlas, and for virtual intracranial EEG, randomly selecting the same number of channels and same number of subjects to calculate the average. And repeating this step 1000 times, we then calculate the proportion of overlap between intracranial EEG and virtual intracranial EEG. This shows an example of comparison of spectral density between intracranial EEG and estimated virtual intracranial EEG from MEG for an ROI called superior and middle occipital gyri. Here, normalized power spectral density is plotted as a function of frequency in log scale. The black line represents the average intracranial EEG of 21 channels within the ROI, and each of the blue lines represent estimated virtual intracranial EEG from MEG for the same number of channels. For each of the frequency where there is an overlap, we plot a blue dot along the x-axis. And for each frequency band, the percentage of overlap is also shown. Here are the highlights of the preliminary result. This slide shows the comparison among different ROIs. First, we show, for example, of ROIs in superficial regions, sorted based on their estimated virtual intracranial EEG amplitude from high to low. We can see that when the ROI is superficial and has good amplitude, such as superior and middle occipital gyri, the estimated virtual intracranial EEG from MEG has a good overlap with intracranial EEG compared to the ones with lower amplitude. As we go deeper, as long as the ROI shows high estimated amplitude, the virtual intracranial EEG and intracranial EEG have a good overlap. For ROIs in deep regions, such as middle cingulate and hippocampus, the estimated virtual intracranial EEG amplitudes are very low and have more dissimilarity with intracranial EEG. Some other highlights of these preliminary results are the alpha oscillation found in occipital, parietal, and temporal regions, beta oscillation found in frontal regions, and delta oscillation found in temporal regions, which were previously reported by intracranial EEG atlas, are also retrieved well from MEG estimated result. Interestingly, we see an alpha oscillation in deeper regions, which is probably coming from signal leakage. So incorporating deep structures in our source reconstruction method might improve this leakage. To conclude, this preliminary result shows that we can assess for which brain regions and for which frequency bands we can reliably interpret mixed source analysis. Thus, this study has the potential to resolve the uncertainty regarding the type of intracerebral activity that can be confidently recovered from non-invasive mixed studies. How this project can contribute to open science community. Firstly, the data used in this project, such as the intracranial EEG atlas to validate resting state MEG data, is openly available. Also, the MEG data will be published according to the rule of Minister of Health funding. Secondly, the software used for our analysis, Brainstorm and BEST, a toolbox dedicated to EEG MEG source imaging such as MEM and WMEM, are open source software. And our group, with collaboration with Dr. Jongma Lina, are active contributors of this open source software. We will provide access to our community to any new developed methodologies in platforms like Brainstorm and CBrain. Thus, sharing of these methods will benefit other groups working on similar source localization techniques. Thank you all for listening. Thanks to CONP and the Faculty of Medicine, McGill University for funding this project. For any questions, I can be reached at this email address. Thank you.